Welcome back to these short talks on improving our programming tools. If you want a proper introduction, watch the first episode in the series. Here we dive right into today's topic, static versus dynamic typing, and how we can resolve a false dilemma. I'll briefly explain static and dynamic for those of you who need a reminder. Then we'll discuss the pros and cons of both styles. And towards the end, I'll show my prototype, which tries to give us the best of both worlds when it comes to error handling and a fast iterative workflow. The prototype has some pretty unique features. For example, you can choose any line and start running the program from that line forward. Some background. Historically, dynamic typing often went hand in hand with interpreted programming languages, and static typing went more hand in hand with compiled languages. But that's a generalization. There's a lot of details and nuance that I'm glossing over here. If you want more details, I can recommend a good talk called The Unreasonable Effectiveness of Dynamic Typing for Practical Programs. Robert Smallshire explores the disconnect between the dire outcomes predicted by advocates of static typing versus the near absence of type errors in real-world systems built with dynamic languages. So, as that talk description hints at, there's an age-old debate here about which type of language is best. People tend to have some pretty strong opinions about it. There's definitely very real pros and cons on both sides. Fortunately, languages are borrowing good ideas from each other. Not long ago, in static languages, you always needed the full type written everywhere, like concurrent dictionary, vector2, tuple, float, string. That was tedious to read and write, even with autocomplete. Nowadays, in C# you can often just write var, so it's less repetitive and looks more like JavaScript. On the other hand, TypeScript is like JavaScript but with optional types, and Python now supports type hints as well. It feels like languages are gradually approaching each other. I think this convergence is good, and I have some ideas for further convergence in the area of error handling. We will look at an example of errors in two languages. Here is Visual Studio Code with some simple JavaScript. If true, we print hello world. Else we have a planet variable here, which in this case is Mars. Then we print hello planet. Oh, I misspelled it here. But that doesn't matter, because JavaScript doesn't do any checking of the whole program. If I press play, we see the output hello world. So we executed the true branch, and we never got to the else branch. Now, if I change so that we'll execute the other branch, what happens? Now we get an error, because planet is not defined. So this is a runtime error. It happened when we reached that line, when we reached that misspelled variable, the error triggered. Whereas if we didn't reach it, it wasn't a problem. That's typical for Python, JavaScript, and this family of languages that have very flexible dynamic typing. For contrast, let's look at C#, which will represent the static language family. Same program, same spelling mistake. If I try to run this code, I can't, because there's an error. The name planet does not exist in the current context. So C# and other languages like it refuse to compile due to an undefined variable, even in a branch that's never taken. There is some nuance here, because it's not like C# will catch every conceivable error at compile time. That's impossible. It just catches some of them. An example of something that it doesn't catch at compile time would be index out of bounds in an array. Index out of range exception. So it compiled successfully, it started to run and printed hello who, but then crashed at runtime. And on the other hand, even in dynamic languages, some errors are caught immediately. An example is a missing parenthesis. If JavaScript really truly ran line by line until it encountered an error, it would print hello who. But that's not what happens. It doesn't print anything. So that's a parse error or syntax error. And every language that I know of will parse the whole file before starting to execute it. Now let's think of the pros and cons with both styles in a more realistic example. Imagine that we're developing a new feature within a large existing codebase. Maybe drawing a planet in ASCII art. There's already a draw circle function, but it's missing some features. We can reuse it if we improve it. Add support for outline versus fill character. But as we add parameters to the function, we're breaking all the existing call sites. But we don't care about that right now. We'll fix that later. In dynamic languages, that's totally fine. They allow us to focus on our new feature and test it without fixing unrelated parts. We can experiment, we can run the program and test our new feature many times until we're happy with it. In static languages, that's not fine. The compiler won't let us run broken code. We're forced to fix all the call sites before we can test our changes, every time. That slows down our experimentation. We'll probably waste time fixing errors caused by experiments that don't end up surviving in the end. But then comes the twist. When it's time to finalize and wrap up our change, we want to fix everything we broke. Unfortunately, dynamic languages aren't going to help us find what's broken. So we'll need unit testing or manual testing and just hope and pray that we find everything. On the other hand, that's where static languages shine. They won't stay silent. We can refactor with confidence because the compiler will yell at us and help us find all the things we broke. So that's great. Let's illustrate what we just said in a diagram. When does the error stop the program from executing? Early or late? On the left we have, for example, parse errors. They are always caught early before anything runs. And then on the right we have runtime errors like index out of bounds or null reference that are caught only when they happen. But then we have things like undefined variables that don't clearly belong to either side. Depending on the language, those are caught either before running, like in C#, or at runtime, like in JavaScript. But here's an insight. There's actually two dimensions. The other dimension is, when does the computer tell you about the error? Early or late? All languages today seem to fall into opposing quadrants. Static languages tell you early and force you to fix it early. And dynamic languages tell you late and don't force you to fix it until late. I said before it can harm your productivity if you're forced to fix a lot of errors before you can run the program at all. So in that sense, the right side is better. The static languages help you refactor with confidence because they tell you about the error early. There's no harm in that. Earlier is better. There's an empty quadrant here that would be useful. We can imagine a language that tells you about errors as early as possible, but it doesn't force you to fix them early. So I propose that a language should let you choose which quadrant to put these errors in. So while you're experimenting, you set the language to be lenient. And when you want to finalize your feature, you reconfigure the language to be strict and you clean up. This concept with two modes is a bit similar to debug builds and release builds. So I've implemented that to prove that it's possible. I've implemented it in a toy language, in a prototype programming environment, not the real deal. I might do that someday, but I have so many other ideas I want to get out first. But this should be enough as a proof of concept. I've imitated the layout of Visual Studio Code here. So here is my code. And when debugging, here are the variables. Here's a call stack view, and here is the output. I have the same program as before. Let's run this. I get an error. Line 9, undefined variable planet. Yeah, because I misspelled it. But check this out. If there are static errors, don't run. Let's click the arrow here and change to if there are static errors, warn, run anyway. So let's try it now. Start. Now it ran. It printed hello world. But we still got a yellow warning at planet. So the compiler doesn't have to be completely silent about these problems that it sees. And I think that's really helpful. So my suggested workflow is that while we're actively iterating on something, we should use warn run anyway. And experiment with that draw circle function and break all the other call sites and run our code anyway. Then before shipping or on our build server or before merging a pull request, use the don't run option. So I could end here, but I also implemented a few other features that really take the convenience to the next level. By letting us run half-broken code, this tool would speed up our iteration, but it's still annoying to test. I have to log in with username and password, then I have to navigate some menus and enter some data to get to the code I'm working on. It's hard to reach. And in my test I notice a bug. Then stop the program, change the code, and then run again from the start. Log in again, navigate some menus again. Tedious. Sure, we could change the code to make it more easily testable. That would save time in the long run, but it costs time to set up initially. So instead, we often suffer through the slow testing over and over again. Wouldn't it be great if we could just say, run from this line? So I implemented that. Click a line number in the left margin to set the start point. If I start from this line, we print drawing, and then we try to print radius. But since we started from down here, we never executed this line above, where radius was defined. So we don't have that variable. We get the runtime error, undefined variable radius. Of course, this kind of error will happen a lot, so then what? We should have a chance to fix it. Look in the variables and values box in the top left. Currently, we only have one variable, radius, but its type is unknown and it has no value. This message says that when execution reached line 115, we tried to read the variable radius, but we haven't yet visited its declaration at line 112. If you enter a valid value for the undeclared variable, you can continue. Here's the input box, so I can write, for example, 7. You'll see the color here change from red to green to show that the problem is solved. So if I type that and hit enter, now it's going to continue executing. So now it prints radius, so that works. Then it stops on the draw circle call, because functions can be reassigned in this language, and then happily draws the circle. What if there's a lot of undefined variables? It still seems tedious to manually enter a lot of variables every run. It should be possible to reuse a value from previous runs. When we ran the program normally from the start, all the variables got values assigned. But normally in most editors' languages, as soon as we stop the program, all that data is gone. But what if we save that and reuse it? Then, when I start from this line and reach any undefined variable, my prototype will automatically suggest the value it had last time. This idea isn't fully developed yet. Currently, I still have to press enter once per variable. This is still tedious. You probably want a load everything button. But for that, it has to be trustworthy. Currently, it doesn't always do the right thing. The prototype has a single snapshot from the old run and simply matches up old and new variables by name, which works in the common case, but fails if the code has changed a lot or if you start from a very different line. A future version could be more intelligent and reliable. Also, here we got an error when we reached edge char, because we hadn't executed this line this run, but with a bit more static analysis, you could totally see that edgechar is always going to be equal to x. There's no other option. In that case, the debugger shouldn't even stop here. It should just immediately see that edgechar is supposed to be x and move on. I think this start running from line feature would really help me iterate faster when working on something deep inside a stateful program. That's it. That's all I wanted to show. You can play with the prototype on my website at emilprogviz.com/debugger. Now I want to give credit to the people who unknowingly helped. Because, of course, I needed some language to build my features in. The language in my prototype is based on locks from this book Crafting Interpreters by Robert Nystrom. If you've never made a language before, which I had not, it was a great introduction, so I warmly recommend this. I'm not using exactly locks. I started from it, and then I changed the semantics a bit. As you saw, my prototype runs in a web browser, so of course I wanted locks implemented in JavaScript. Rather than implementing it myself, I found this JavaScript implementation of locks here by David H. Friedman. Then I changed it a lot, but you provided the starting point. Big thanks to David and Robert. If you found this thought-provoking, please comment. Did it give you any new insights? Can you improve on these ideas? What would make it even better? Look beyond the false dilemmas and the eternally raging debates of the programming world. Think constructively. What are the pros and cons of both sides, and can they approach each other? Don't just design new languages. Design new IDE features too, and let them go hand in hand. And don't be afraid of implementation complexity for the language or the IDE. It's worth it because millions of people are going to use it. And share the ideas openly.